All right, hey guys. I hope everyone's in the right place. Hey, again, thanks for attending our talk. This is the 25-minute turbo talk on an embedded system called Twine. Embedded devices are increasingly becoming a focus of security research. And if you've ever worked with or tried to perform your own assessment of an embedded system, you may understand some of the challenges that you're faced with and some of the workarounds that you came up with. But if you haven't, hopefully after this talk you'll have some insight. That's really how we wanted to frame this talk. Because we're security guys, we're software security guys. We don't know much in the hardware aspect of security, so this was something that we were really interested in getting into. So of course this is a turbo talk. If you have any questions, please hold them to the end of our talk. So about us, I'm John Chittenden. This is Anson Gomes. We're security consultants with ISEC Partners. We're based in New York. We're based in New York. This was a project that had 3 members of our team. The other was Glenn Saunders, who unfortunately couldn't attend Black Hat. So just sort of like a backstory on Twine. Twine came up as, someone just sent us a Kickstarter link, one of our colleagues, and we were really interested in it. We watched the video. We said, hey, this is a cool product. Let's buy one and poke around with it and see what we can find. So today we'll talk about Twine, what it is, how you would use it. Then we'll also just talk about our setup, our analysis, what we found, and then ultimately some solutions for this. So what is Twine? Twine is a embedded system that was created by a startup in Austin called Super Mechanical. And essentially their marketing material suggests that it allows you to connect your things to the internet. And without a nerd degree, which I think is kind of cute. But at any rate, essentially what it allows you to do is detect changes in your environment, wherever Twine is, and then communicate these changes to you. So as a use case example, let's say your basement was prone to flooding. You may connect a moisture sensor to your Twine, and then once that's connected, when it detects wetness or moisture, it'll communicate that to you. So you can break it up into a couple of components. The first is the input. So for Twine, you have your environment, and the sensors are constantly polling. You have a variety of sensors here, and it's constantly polling and then packaging up and sending this out to the Twine backend. Now the Twine backend allows you to create this conditional rules. So if a certain condition is met, then perform this certain output. So the output could be Twitter, SMS, text messaging, whatever it is. And this isn't an exhaustive list. Super Mechanical is constantly improving Twine, updating it, and rolling out new types of sensors. So why Twine? Well, it was a black box. It was interesting to us. We didn't know much about it at the time, and it had a nice overlay of software security and hardware security. To that end, the embedded system in it, has the wireless access point, right? It also has a web server, 2 different types of firmware on there, and some other really interesting components. So as far as like the attack surface goes, it's varied, right? There's a lot going on here. There's a lot of interesting components. And as I mentioned, we're software security guys sort of delving into the world of hardware security. So it's a nice little overlap. As far as the application components go, you have a web server. So when you configure Twine, you flip it over, it becomes its own wireless access point, and you can connect to that. Once you've connected to it, it has its own local web server where you will actually set up and configure the device itself. So once it's configured, you flip it back over, it connects to your wireless access point, and then have fun with it, right? So as far as like the other components go, the rule sets, these are the conditional rule sets that I mentioned earlier, and then it's also communicating over TCP and UDP. As far as the hardware components go, you have this GainSpan system on a chip. This is really the brains of Twine itself. Within this GainSpan chip, we'll show it later, but it's got its own wireless access point, and this is really where all that functionality is coming from. On the Twine board, you also have data storage, its own Twine firmware, and then of course your variety of sensors. So just a quick recap of Twine. We have this black box, which is really just a green box, but if you remove this sleeve and go a little bit deeper, here's Twine in all its glory, naked. And here right here is the gainspan system on a chip. If you look up here on the top right, you can see the antenna, and that's where the wireless functionality is. You can also, if for a keen observer, you might notice the micro USB input. That's mostly for powering it. That's not for debugging. And then also for on the gainspan chip, you'll notice the pins on the right and left of the chip. That'll come up again later, but that's where your UART and JTAG and a bunch of other interesting little pins are. On the side here, we have a sensor, and it's connected to Twine via 3.5 millimeter jack. Yeah.
All right, so like John said, Twine was a black box device, and we knew nothing about it. The only thing that we knew was that Twine communicated with Supermechanical's web servers. It monitored the environment, through all the sensors, gathered all this data, sent it to the Supermechanical servers. So we knew that there was some sort of communication, and that was like our entry point. We wanted to target this and get into the middle of this communication, either passively sniff it or actively man in the middle of this communication through with a proxy and try playing around with it. So this can be a little tricky at times, if you want to set up something. Twine is a wireless sensor block, and if you want to set up, if you want to man in the middle of this, you want to man in the middle of the actual access point, and we've got to create our own access point for this. If you want to, get rid of all the noise on the network, all the noise that's been sent across the wire. So this can use, you need some special hardware as well as software for this. You need something, in terms of hardware, you need a chipset that supports master mode, and software, you need host APD, which sets up the access point. You also need a DHCP server for leasing out IP addresses. IP tables need to be configured to allow proxying as well as forwarding traffic between the device itself that's connected to the internet. It can be a little tough, and we decided to go with the Wi-Fi Pineapple, which does all of this out of the box. It sets up an access point and uses IP addresses. It also, with a little tweaking, you can get it man in the middle network communication. So using this, we had a neat little setup. This was our setup. We had Twine talking to the Wi-Fi Pineapple wirelessly, and the Wi-Fi Pineapple was connected to the Wi-Fi adapter of our laptop. And all the proxying and monitoring of this network traffic happened on a laptop, which is connected to the internet using the Ethernet port. We configured IP forwarding so we had to create a route between the Ethernet port as well as the Wi-Fi adapter, and we use IP forwarding to allow traffic between these two adapters. If you want more information about this, there's a neat little article that I've written on the ISEC blog, and you can use that for more information. So we had all this set up. We were now man in the middling the actual network, the communication between Twine and its Supermechanical web server. But we still, we ran into a little bit of trouble right there. Twine communicates over a couple of high order ports, nothing to be concerned about. But proxying really didn't help much, because Twine, some of the traffic between Twine and the Supermechanical servers is actually encrypted. And so we basically ended up looking at all the packet captures that we'd captured using Wireshark. That was what we based most of our analysis off of.
So right, as Anson mentioned, at this point we have a bunch of wireless PCAP files. And we understand that Twine is at some level communicating with the Twine backend, but we don't know how. We don't really understand the protocol. So we began poring over the Wireshark captures, and you had these data blobs that looked a lot like this. Now, granted, you would have the ASCII representation of some of these characters, so this might pop out to you. This is actually POLL, so P-O-L-L. And if you think about it a little bit, if you were performing malware analysis and you wanted to know how a piece of malware communicated with the CNC server, you need to take a step back and realize that, hey, this is a well-defined language that it's speaking, right? It needs to know how much to parse into the hex stream or the binary stream and understand, all right, this is the field for the type of message, a POLL message. So to fill in these sort of blanks and understand the protocol, we would begin looking further back into the the prefix values here. So here we have a 4. This actually signifies the data type length, which is the next 4 bytes are 5. So it's an integer. It's an integer type. And that's actually the length of the poll message with a null terminated string, right? So if you take that simple example and apply it to the rest of it, things start to become more clear and you start to understand how Twine is actually working. So the poll message itself is essentially just a heartbeat with the Twine backend. And here we have a number of different fields, the Twine identifier, which is unique to every Twine, the message type, the firmware version, and the RSSI, which is the received signal strength indicator. And that's, again, just the Wi-Fi signal strength with the access point. And now the server will respond in a couple of different manners. The first is just generally a null, which does do nothing. And then the second, or the last two, wake up and ARM flash, are linked together. It's essentially waking up the Twine device and preparing it to be updated and flashed. So in addition, we have the UDP data message. And as Anson had hinted at, there is some sort of encrypted magic happening. Well, it turns out that the UDP data message is all the sensor data being transmitted to the Twine backend. And again, you know, if we look back here at the TCP messages, they follow a very similar pattern. We have the Twine ID, the message type, so this is a UDP data message. And then we have this huge encrypted blob, right? Well, it turns out that this encrypted blob is all the sensor data, everything on the onboard Twine device and everything connected to it. It gathers this all up, encrypts it, and then packages it and sends it out to the Twine backend. So just to recap, we have 2 avenues of communication occurring here. We have one from the server to Twine, and then one from Twine to the server. Twine to the server is occurring over TCP and UDP. It's roughly every 45 seconds. And from server to Twine, this is predominantly or only over TCP. And we have 3 different responses: null, wake up, and ARM flash. And now the updating process for the ARM flash, this could be for rules, if you were pushing down new rules to Twine, or if you were to update the actual Twine software.
So we've seen that some of the data sent between Twine and Supermechanical is actually encrypted. But we've also seen that at least the poll message isn't. You know, we can see the actual poll message and the responses sent from the Supermechanical servers, and that's all in plain text. So this here is a screenshot of a packet capture where, you know, when we updated the rules on the website, it sent down these rules to the Twine device itself, and here, if you look a little closer, we see Jonathan's email address as well as the message that Twine is supposed to send to his email account. You know, this is personally identifiable information, and it shouldn't really be, you know, publicly accessible to anyone that's sniffing on the network. You want to protect this with some sort of network, you know, network security protocol, and just prevent any unwanted information from being displayed or accessible to anyone passively sniffing on the network. Well, this is plain text message. What about encrypted message? We know that the sensor data that's being sent across from Twine to the servers is actually encrypted. But I mean, the simplest thing in an encrypted message is just replaying that. And that's exactly what we did. Let me pull up a real quick demo right here. So this is our script, and we just basically called it fake Twine, and we sent you know, like a lot of data from us to the servers. This is a baseline message, and you can see here that it updates. You can see that the last update was 5 seconds ago. If we replay the message again, you see that it has changed, and it is it's, you know, it's detected that Twine sent a message like just a second ago. In the same way, we can get, you know, after capturing sensor data, we can get it to replay all this sensor information. Like we can tell, you know, we can trick the server into thinking that Twine is wet by just sending it a packet data, a UDP packet with the sensory data for it being wet. The same way, if it's dry, you know, if we change it to dry, we see that it's dry. So this is just replaying all the packet data, and I mean, the first thing when you're building a protocol, you don't want to basically replay all this, you don't want it to be susceptible to a replay attack. It's networking 101, and things like this should be avoided. So that was the encrypted data, but what would be sweeter is if we could actually try getting the encryption key. So we have access to Twine, and we thought that maybe interacting with it, getting terminal output or access, if we could send it some commands or try interacting with the file system, maybe we could get somewhere with this. So that's exactly what we did next. So we tried getting terminal output, and in order to do this, you need to understand the hardware. We knew the serial numbers of the chips. We knew everything about the hardware on the board itself, and a little googling around got us the data sheets for these chipsets. And when after reading all these chipsets, we realized that Twine has the GainSpan chip has a lot of interfaces that you can interact with. Here is a screenshot of the pinout from the datasheet, and you can see it has a couple of UART ports. It's got JTAGs as well, and if you look on top, it's got the SSPIs as well as GPIOs. Interesting interfaces that you can interact with Twine, and we decided to stick with, being software security profession, we decided to stick with the easiest, which is the UARTs, and we use the hands for that. We use the fingers and connected the pinouts, and bang, we got terminal output. So if you look at this, it's pretty standard. It's booting for the first time. You see the version ID, the version number, which is the date and timestamp, which you've also seen in the packet captures. You also see the Twine ID. This confirms our initial thought that that was the actual Twine identifier in the packet. And you see the MAC address as well. What is interesting is the PSK. Now, when I see a PSK in any output, it's always okay. What is that? It's supposed to be something sensitive. And if you go down further, you see that Twine is actually trying to connect with the Pineapple SSID, and the PSK is valid. So putting two and two together, you can come to a conclusion that the PSK is the actual encrypted password for joining the Wi-Fi network, and that's actually true. At some operating systems, you don't even need the password. You can just input the PSK and get connected to the network directly. Additionally, you can also see that it's trying to connect to super mechanical servers, sending it a poll message, UDP message as well, the size of the UDP packet that it's actually sending. Some of this is a little sensitive, including the PSK, and you wouldn't want to have a device that's in production that's displaying all these messages that should be accessible only in debug mode or something like that. So this is terminal output, and just to recap, you need to find 3 pins: ground, transmit, receive. There's a nice article that shows you exactly how to do that. And once you've located these 3 pins, you need to connect it to the laptop using a USB to serial a UART to USB serial USB connector. Make certain you have the drivers installed to interact with the hardware. And you also need to use Teraterm. You need to use a terminal emulator for printing output, something like Teraterm or Xterm. And you also need to find the baud rate for the device. In Twine's case, it was 115200. Now, there is no easy way of finding the baud rate. It's through trial and error. There's a finite number of baud rates, and you just have to cycle through each and every one of those so you get the correct one. You can write a script. There are scripts out there which do that for you. But once you have all this configuration data, you get terminal output. So we now had terminal output, but it was a read-only terminal. And instead of messing around with any of the other interfaces, we thought about what about dumping the firmware? If we can dump firmware, maybe we could get something sensitive, maybe something interesting would pop up. And that's what we did next. So we used some special hardware, which is an 8-pin SOIC clip and a USB to MPSC serial cable. And you need some software to talk to the flash memory, and that's libmpsc. So using this combination of hardware and software, we dumped the actual firmware from the device itself. And then we had to analyze it. So we used binwalk for this. What binwalk does is it detects the actual file segments in the offsets for the files in that actual firmware, And you can use Binwalk to extract those file chunks. So that screenshot that you see right there is Binwalk being used on the Twine flash that we dumped, and you can see that it is, it's extracted about 5 gzipped files, which were the actual HTML web pages that Twine sets up with the web server, that John mentioned earlier during the setup process. The GIF image is the actual Twine logo, and the LZMA compressed image. Now that's interesting. That was a binary file that we could then load up into IDA and start reverse engineering it. I'm not going to talk about this due to time constraints, but that's one side of the firmware that we actually dumped and started reverse engineering. There is another firmware that you can dump as well, and that's through the packet capture. So John mentioned that there are 2 types of updates that are sent down to Twine itself. One is a hardware update for the system on a chip, and the other is the firmware that's pushed down to Twine in when you make an update to the rule sets. And so this screenshot is a packet capture of the firmware being pushed down to Twine. It starts off with Twine sending a poll message, the server responding with an ARM flash, and Twine says, all right, let's start the flash, and there's a CRC checks, and it then sends this entire chunk of data, which is a firmware. And we use dpacket and Python to extract this firmware. Again, once you've extracted it, it's all about reversing that firmware. And that's where we're at this point.
All right, so to sort of wrap things up, the Internet of Things is one of these buzzwords that's around a lot, and security research is definitely focusing on embedded systems. As far as like small startups go, they're starting to get into this space a little bit more, and you're seeing more devices and more things being added to this Internet of Things. So, we find it necessary for people to sort of understand some of the security and privacy risks. In Twine's example, they could simply just extend their current crypto implementation to protect the user data that's being leaked. Then also, as far as their protocol goes, fixing a replay attack is, should be fairly trivial, I would think. Just include some sort of timestamp or nonce and have some sort of logic to verify that. That said, also don't print sensitive data to consoles on production devices. And with that, we're sort of done. So if you have any questions, feel free to ask now or contact us via email or Twitter. Thank you.